Hello everyone. For this tutorial video, I'd like to introduce rotational momentum, which is more complicated than its linear form, exactly like how rotational motion is more complicated in general than linear motion. Since we have figured out all of the rotational versions of linear motion variables, it would be fair to guess that rotational momentum equals rotational inertia times rotational velocity. Exactly like how linear momentum equals linear inertia times linear velocity. The conventional symbol for linear momentum is capital L, which, like many rotational variables, like theta for angle, is mostly an arbitrary choice that does not have a logical etymology. But if you wanted to attribute it to something, we could state the capital L stands for Leonhard Euler, who was a genius mathematician and physicist who first described the dynamics of rotating bodies in detail, in addition to many other things in the field of mathematics. Just like linear momentum, angular momentum is conserved provided there are no torques acting on an object. So for example, if you spun with your arms wide at first, and then spun with them inward, you would notice that you would spin faster as you are easier to rotate. But the momentum stays the same, because while the moment of inertia decreases, the angular velocity, i.e. the speed of rotation, increases, so these two cancel out and the momentum remains the same. If you paid close attention to where I was rotating, you would see that I was rotating relative to the horizontal center of my body. And in general, any object that rotates either vertically or horizontally with reference to their center of mass, such as this pen, gains an increase in rotational momentum, or decrease, as the case may be. At this point, I'd also like to bring up rotational friction, which is the force that causes rotating objects to stop spinning, exactly like how linear friction works. For example, if I spin this pen, it does not spin indefinitely, but stops, due to the force of friction acting upon it. A more massive or heavier spinning object will stop spinning more greatly, i.e. experience more friction, for the same reason that a more massive object experiences greater linear friction. However, rotational friction is more complicated, not only because of the motion involved, but also because the material involved comes into play as well as the overall mass. For example, if an elastic object, like a car tire rim, rolls, it will tend to lose more of its motion to squishing or deformation than a more firm or rigid object. In contrast, with linear or sliding friction, this is not as much of an issue, because of how an object tends not to squish as much when it slides versus when it rolls. In the next tutorial video, I will explain in a more rigorous fashion how gravity works, including Newton's law of universal gravitation and the Henry Cavendish experiment that later demonstrated this concretely. Don't forget to subscribe if you found this video informative, and make sure to see other tutorial videos, and follow me on either Facebook or Twitter for more content.